Hello, dear students. This is your professor, Lázaro Pino, and today I wanted to explain a little bit about the atomic structure, what is an atom, an ion, and the atomic structures, the electron, proton, and neutron. And also, we are going to speak about the atomic theory, and we are going to see some typical exercises. But first of all, let me remember that this is the last task or the last chapter for the next and first exam that will be the following week. Well, after that, let me begin by explaining that the atom is the basic building block of all matter and of course of chemistry. And also that atoms can combine to make molecules. We can say that the atoms cannot be divided into small particles. The molecules, yes, they can be divided into the different atoms that they are made of. The atom is almost empty space, because it's made of a cloud of electrons, and almost all the mass is centered in the middle of the atom, what we call the nucleus of the atom, and it is made of protons and neutrons. The protons and neutrons form, as I told you, the 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 nucleus of the atoms, while the electrons are in a cloud around the nucleus. Then most of the mass is here in the nucleus. The rest is empty space. As you can see, the electrons are negative charged, while the protons are positive and the neutrons have no charge. And if we compare the nucleus with the electron cloud, you can see the nucleus is a small, very small part. The electrons are in shells around the nucleus. They are negative, as I told you before. The number of electrons is equal to the number of protons that are positive, so that the atom is neutral. As you can see, the number of protons is equal to the number of electrons for different types of atoms. If a neutral atom loses electrons, makes a cation, that is a positive ion. If an atom gains electrons, then it makes an ion or a negative ion. For example, if you go to the periodic table, this is the symbol of the element. In this case, is carbon, capital letter. That you can see a big number that is the mass number, and a small number that is the atomic number. We are going to see what represents every of these two numbers that are very, very important. So if you go to the periodic table, you can see the symbol of the element, a big number that is the mass number, and a small number that is the atomic number. Even though we say that we have an element with a specific name, we can find different types of atoms. The difference is the number of neutrons, because the number of protons is always constant for a type of element. Then the number of protons is what makes possible to identify a specific element, but not the number of protons. Then these three atoms of hydrogen are hydrogen, of course, but they are different because they have different number of neutrons. That's what we call isotopes. Isotopes are atoms of the same element with different number of neutrons, and of course, different number of atomic mass. Well, the first person that gave an idea of a real idea of what matter was composed of was Democritus. He named the atom to the small particle that made every type of matter. He said that they cannot be divided, and they are hard, small, and he represented this like a circle. And he said that we can identify different type of matter for the type of atom that makes this type of matter. Even though he was right, well, his theory was not accepted during a long time, and was accepted the Aristotle's idea that matter was made of fire, air, earth, and water. Well, nowadays we know that Aristotle was wrong, while Democritus was right. It was not until the 19th century when John Dalton explained a new theory about the atom. He said, all matter is composed of atoms. Atoms of each element are the same size, mass, etc., but are different from atoms of other elements. He was right. Atoms can't be subdivided, cut, or destroyed. Well, atoms cannot be divided, but let's see what happened with the atom. And he explained that atoms were tiny solid balls. This was the way he represented an atom. It was in 1897 when Thomson used a cathode ray tube to reduce the presence of a the presence of a negatively charged particle, the electron. He discovered the electron. Then he said, well, the atoms are composed of a positive part, and inside of this positive mass, we can find the electrons that are charged particles, like, and they represent light. um, the he says that it was like a pudding, and then this was or a chocolate chip cookie. Suppose it is a chocolate chip cookie. Well, the particles, the electrons, the negative particles were like the chips of chocolate into the mass of the cookie that for him was represented as a positive charge. But after that, one of his students discovered in 1918 the proton, and it was Rutherford. He could separate or detect it, that there were not only negative charges, but also positive charges. And he continued doing experiments, and he made this experiment that is known as the gold foil experiment. Why? Because he put a gold foil, very, very, very thin, in the in the in the way of a beam of alpha particles. Alpha particles are two positive particles. And he discovered that most of the alpha particles went through the foil. Well, positive and positive repel. Then the mass of the foil is not positive as was represented by Thomson. Thomson said that everything was positive, and then the chips, the chocolate chips, were the negative charges. If matter were, if the atom was this way, then most of the particles, the alpha particles that are positive, must be repelled, and this was not the case. So most of the atom is empty space. Some of the particles well deflected, only a small group. Then it means that the nucleus is positive charge, and that's why some of the alpha particle were deflected when they went very close to the nucleus of the atom, and only a few were traveling back. It means that they bump into the nucleus, and positive repel. So the alpha particles came back. Well, this is the well-known Rutherford's gold foil experiment, and because of this, he said that most of the atom is empty space, and the nucleus is positive charged, and is not, is only a very small part of the atom. Because of that, he represented the atom as a nucleus, a small nucleus, and around this nucleus there were some negative charges, the electrons surrounding around this nucleus. This is quite different from the idea of Thomson and his chocolate chip cookie. But after that, a scientist born in 1913, then in the 20th century, last century, he said, or he explained that the atom has the same model as the solar system. And he proposed the planetary model. Then the nucleus of the atom was like the sun, and the electrons were around the nucleus in a specific areas where, like the planets around the sun. Well. He discovered that every orbit where the electrons were has a number, and they have a specific energy. The difference of energy between one level and another level was directly proportional to the frequency of a transition of an electron from one to another level of energy. Well, let me stop into here. What you need to remember, Bohr represented the atom using the planetary model, where the nucleus was in the center and around it were spinning the electrons in a specific, very specific orbits. And every orbit has a specific energy. Well, let's continue. Wow, what was the problem? Well, if the electron were spinning around the atom, it was supposed that because of the movement, the electron was losing energy and changing the position around the nucleus, and at a certain time will bump against the nucleus. Wow, during that time, the physics were in a big trouble. Nobody could explain why the electrons didn't bump into the nucleus. And it was until Bohr that he says that the atoms has the electrons in a specific orbit, and this energy was an exact quantity. We could quantify the energy of the different levels, and he explained that the electrons remain in the shell and never gains or loses energy. Well, it's a good idea, but in order to explain that, he used he used or he quantified the energy of the different levels using the atom of hydrogen. And he get an equation in order to quantify the levels of energy. But what happened? That this equation was pretty good to explain the atom of hydrogen that has only one electron. But when he tried to use this equation to explain the other atoms with more than one electron, it failed. Was he wrong? Well, let's see. After that, somebody or a lot of different theories were discovered. Well, not discovered is not ideas. A lot of new theories came and tried to explain why the atom has this level of energy. The electrons move around the nucleus and didn't lose or gain energy. And it was until the quantum mechanical model that it was explained that the energy, first of all, that the electrons are not in a circle around the nucleus. The electrons were in a space around the nucleus where we can find with a big probability this electron. Then it was not just a circle, it was a cloud where the electrons could be found. And there is an equation that explains how we can quantify the level of energy, and also an equation where we can find the space where it's more probably to find the electron around the nucleus. I'm not going to explain this because it's too deep to be studied at this level. Only I want you to understand that the quantum mechanical model is the only theory that can explain the structure of the atom until we know nowadays that we have the protons and the neutrons in the center of the atom, making what we call the nucleus. And around the nucleus are the electrons in orbits that are the most probably a space where we can find the electron. As you can see here, for example, an atom of carbon has 6 protons. Protons are positive and has 6 electrons. In this case, an atom of carbon has this isotope in a specific, because carbon has different isotopes, has 6 neutrons. Neutrons are nor positive nor negative. They are neutral. And because the number of protons and electrons are the same, they cancel out, and the atom is neutral. The atom is neutral. You can see that oxygen has 8 protons, positive charges, and 8 electrons, negative. Sodium, 11 positive charges and 11 negative charges. Chlorine, 17 and 17, and uranium, 92 and 92. Then conclusion, the atom is neutral. Why? Because the atom has the same number of protons in the nucleus than electrons. If you go to the periodic table, as I told you before, the atomic mass is the big number that you can see beside the symbol of the element. The atomic mass is the sum of protons and neutrons and represents the mass of the atom. While the atomic number is the number of protons. Listen to this. The atomic number represents the number of protons. Oh, but as we know that the atom is neutral, the number of protons is equal to the number of electrons, then we can say that the atom of carbon has also 6 electrons. But the atomic number, and I want to repeat it once again, is the number of protons. Let's continue. Here you have the atom of iron. You can see that the atomic number is a whole number, the symbol, the name of the atom. But look at this, the atomic mass is a decimal number. Why? We have pieces of protons and pieces of neutrons. No, it's because it's the average of the atomic mass of the different isotopes of the atom of iron. What is the meaning of that? Well, the average is the sum of the multiplication of the atomic mass of an atom times the abundance of this element divided by the number of isotopes. That's why we represent in the periodic table an average. But when we are going to do an exercise, you have to use the specific atomic mass for the specific isotope that I am giving you. Very important, this concept. Well, isotopes, look at this. Hydrogen has 3 isotopes. One that consists in only 1 proton, one that has a neutron, and one that has 2 neutrons. Then when you get the average of the atomic mass of these 3 isotopes, you will get the average of the atomic mass of the element, and that's the one that we represent in the periodic table. Well, here you have an exercise. I want you to fill the blanks. Well, boron has 5 protons, and the atomic mass is, or mass number is 11. So 11 is equal to protons plus neutrons. If I have the number of protons that is 5, we can find out the number of neutrons. Of course, is 6, because 5 plus 6 is 11. In this case, I am trying to find out the number of electrons for potassium. Well, you know that the atom is neutral, so the number of protons is equal to the number of electrons. In this case, we need to know the atomic mass or mass number. Well, is protons plus neutrons. Then it will be 54. In this case, I am trying to find out the number of protons, same way. If I know the number of electrons, I know the number of protons. In this case, I am trying to find out the atomic number. Or the atomic number by concept is the number of protons. So it is 18. Here you have an exercise. You can stop the video and pay close attention to this exercise because you will have a lot of this during this chapter. Well, this is a periodic table. This is not the first time you see it, but I want you to know that the periodic table is divided into representative elements that are these ones in groups 1, 2, 13, 14, 15, until 18. These are representative elements. The middle ones, these ones, are what we call transition elements. And here below, we can find the inner transition elements that are divided into lanthanides and actinides that are perpendicular to these positions. Then you can see then in a perpendicular to the slide, the surface of the slide that you are looking here in my representation. The big number represents the small number represents the atomic number, and as you can see, we order the atoms according with the atomic number. Look, number 1, number 2, number 3, 4, 5, 6, 7, until the last one that is not yet discovered, or is not discovered yet. It is supposed to be here, but nobody discovered this element yet. Then be careful. The periodic table is in the order or the increasing order of the atomic number. And as I told you, we have the green ones are representative, the blue ones are the transition metal, and the red ones are the inner transition metals. The groups are the columns, and the periods are the rows. Then here we have period 1, period 2, period 3, 4, until 7. And the groups are from 1 to 18. We also can divide the elements into metalloids, that are the green ones, non-metal, the yellow ones, and metals, the blue ones. Here you can find what we call a zigzag line that divides the elements into metals and non-metals. And in between, we have the metalloids. When an atom loses electrons, they make a cation. That is a positive charge atom. And when gains electrons, makes a negative ion or an anion cation positive, anion negative. Cation lose of electrons, anion gain of electrons. Here you have, for example, the atom of magnesium. It has 2 plus 8 plus 2, 12 electrons. But when the atom of magnesium loses 2 electrons, make what we call a cation. That is positive 2, because has 2 electrons less, so has 2 protons more than electrons, plus the 2 electrons that are released. Somebody will gain these electrons, of course. Remember that when somebody loses, another one gains. The cation has the same name as the atom. The magnesium atom, magnesium ion. But the anions change the ending by "ide." For example, fluorine, fluoride, chlorine, chloride, bromine, bromide, and so on. Here we have oxide, peroxide, sulfide, nitride. Well, that's all what I wanted you to know until this moment. Remember that this is the last chapter for the first exam that will be not this Monday, but next one. See you later. Bye.